So let's now talk about classifications using likelihood functions. So we talked about a very primitive power-based speech detection system just now, in which case we are actually just going to be recording a speech signal coming into a computer and calculating the short-term power. And we can plot the short-term power. In fact, what we need to do that, first of all, is to label the data, because we need a training data set. If we label the condition where there's speech present and their speech is absent, in terms of short-term power, maybe calculated over so many milliseconds, we might come up with something which looks a bit like this when we plot in red the no speech condition power, and in blue the speech present power. And what we see is obviously when you're speaking there's more power in the signal, so you've got the signal level for power is higher than the signal level for silence. And what we need to do then is distinguish this red no speech condition with the blue speech condition, just in terms of the short-term power. So what first thing we're going to do here is actually to calculate the mean and standard deviations of these two labelled classes of data, right? So what we can do is we can calculate the mean and standard deviation, and then what I've done here is to plot the corresponding Gaussian on top of the data to give an indication of what these two distributions would look like if they came from a Gaussian distribution. So looking at that, we can see that actually, yes, there is a fairly substantial difference between these two sets of data points. And we can think of this then as a modelling exercise where we're modelling the two classes in terms of two different Gaussian distributions. Now what we want to do is classify this data coming in, this short-term power, into the absent or present condition for speech, just looking at signal power. So we need to, if we have just the data coming in, these values coming in, we need to choose a threshold value such that if we're below the threshold value, we say the data is labelled as no speech, and if it's above the threshold value, there's speech present. Right, so if the signal is bigger than the threshold, speech is present. If it's less than the threshold or less than equals, then it will be absent. So how can we find this threshold? That's the next question. And one method, and there's many methods of doing this, is to use the idea of a likelihood function. How likely is it that the data came from one or other class? That's basically what we're going to do. So, in other words, taking one class as A and one class as B, what we need to calculate is probability of class A given the data and probability of class B given the data. And then we choose the class with the largest probability as being the class corresponding to the measurements. So basically what we can do then, if we can make this estimate of the probability of data, probability of the class is A given the data, if this probability is bigger than the probability of B given the data, then it's more likely that the data came from class A. And if the probability of B given the data is greater than the probability of A given the data, it's more likely that this data sample came from class B. So what we need to do is to find this probability, this conditional probability of class given the data, and the way we can actually attack this is to start using, first of all, a model. In this case we're going to use a Gaussian model of the data, and we're going to use Bayes' rule to actually get this conditional probability that we need. So let's think about Bayes' rule again. Bayes' rule tells us probability of A given X is given by or equal to probability of X given A multiplied by the probability of A divided by the probability of X. So just thinking about this in terms of our classifier, if we want, let's say A is no speech given the data X can be represented by calculating probability of the data given class A multiplied by the probability that we're actually, what is the probability of class A divided by the probability of the data. And using the substitutions of all the things that we've just talked about in terms of A and B, what we can do is we can substitute in probability of A given the data equals probability of X given A, probability of A. And what we do at the bottom then, rather than writing probability of the data, probability of X, what we're doing is we're going to expand this out like we did previously in terms of terms that we've actually got at the numerator as well. So we can basically represent the probability of the data by expanding it out in that way. What we actually will find is we don't actually need to calculate this term anyway, because we're just going to be comparing probability of A given xi with probability of B given xi, and in both cases we're going to have the same denominator, so we won't actually have to work that out if we actually implement that. So the probability of corresponding class B given the data is the same form as the probability of A given the data, but we just substitute B in where we had A, right? But as you can see, that the denominators are both exactly the same. So when we're comparing this probability of A given the data with probability of B given the data, we don't actually have to calculate the denominators. So if we've got our data and we've labelled it, we have to have a certain amount of labelled training data. So we've got our observations of, in this case, of the power. We have in this case two classes because we've either got no speech or speech. What we need to do if we want to represent this in terms of a Gaussian distribution, and you'd basically have to look at the data. You maybe want to run a histogram on it. Does it look like it could be modelled with a Gaussian? In this case, it will be, because it's basically a chosen example that we're assuming it is Gaussian. If we've got a Gaussian distribution, in order to represent that, we need what is known as the sufficient statistics for that distribution, and then basically just in this case needs to know the mean and the variance in order to represent this distribution. And we need to do that for both classes. So since we know both classes, we've got the data for both classes, we can split the incoming data up. So for class B, all we have to do is we just look at all the values of the data coming in which are from class B and divide it by the total number of them. So if these were just measurements of the power, which are labelled of class B, add them all up and divide by the total number of them. And if you calculate the variance of class B, then we calculate for each data point which we know came from class B, we then take away its mean, square it and add it to all the others, and then divided by NB minus 1 because we want an unbiased estimator. Okay. We then do the same thing for class A. So we can then, in this way, basically model the distribution for the data for class A and the distribution of the data for class B. What we also need to do is we need to calculate the priors of our model. So we need to estimate, what's the probability of class A happening, what's the probability of class B happening. And we can do that just by adding up basically the times it actually occurs. So if we've got, let's say, altogether n data samples of class A and class B, then the probability of it being class B is all the times that actually class B occurred divided by n, right? That's quite simple. So our Bn in this case represents an occurrence, so it's going to be a 1. We can do exactly the same thing for class A, but we also note that probability of class A plus probability of class B have got to sum to unity because they're mutually exclusive events. So we can also quite easily say that probability of A is 1 minus class B. Now what we want to do is we've modelled our data in terms of the variance and the mean of class A and the variance of the mean of class B. We can then say from the Gaussian formula what's the probability of the data point given the model. So what's the probability of X given parameters for A? Well, that's easy. We just use the Gaussian formula, the probability of the data point given the parameters of model A, and the parameters are the mean of A and the written here as a standard deviation, but the variance of A, is just given by the formula that we have for the Gaussian, right? So we just have to put in the values into the Gaussian formula for a one-dimensional case. So we're going to have scaling factor 1 divided by the square root of 2 pi sigma squared for A, multiplied by the exponential of minus xi minus mu A squared divided by, don't forget the minus sign, 2 sigma squared for A. And we can just write that in a slightly simpler way if we just, this is explicitly saying that this data point is conditional on the mean and the standard deviation of class A, but we could just write it in a simplified way, just saying it's just conditioned on being from the model corresponding to class A, and the rest of it stays the same. Do exactly the same for class B, right? So we have to calculate the probability of the data point given it came from class B. But that's not exactly what we want, right? What we want to know is not the probability of the data given the class, it's the probability of the class given the data. So it's probability of, is it class A given the data, or is it class B given the data? It's class A if the probability of A given the data is bigger than the probability of B given the data, right? And similarly, it's class B if the probability of class B given the data is greater than the probability of A given the data. So all we have to do now is just to calculate these terms like we just did. We just use our expressions that we calculated using Bayes' rule. We have to calculate these out. And as I said before, because these denominator terms are exactly the same in both, when we actually do this comparison, we can actually ignore them, which makes life a little bit more manageable.